Okay, so we've looked at the parent exponential function, understand the properties of the graphs of an exponential function, and here we have pictured 2 to the x, which will serve as the generic exponential function because they all have similar shapes. And if we look at this long enough, we'll notice that if I draw a horizontal line anywhere on this graph, the graph of 2 to the x will intersect it only one time. Okay, so the graph of 2 to the x passes a horizontal line test. If you remember back to chapter 2, okay, if a function passes a horizontal line test, then it has an inverse function. 2 to the x, and any exponential function for that matter, has an inverse function. And what we're going to look at today is who is this inverse function, how does it behave, and how can we study it further. Now, before we do anything else, we know that I can take some of these dots that were on the graph of 2 to the x and determine dots that will be on the graph of its inverse function. We just got to flip the x and the y coordinates. And we know that 4, 2 will be on the graph of the inverse. And we know that 1/2, -1 will be on the inverse. And we know that 1/4, -2 will be on the inverse function. Okay, so you can start to see the graph come together. And on the next slide here, I have a more detailed picture of what that would look like with more dots filled in. And in green, you have the line y equals x, which is supposed to serve as a mirror. And if I turn this sideways so that that line is vertical, you can see definitely mirror images of 2 to the x and this new function, which is its inverse, which we don't have a name for yet. And that's what we're going to look at today, is what is this function called, what calculations can we do, etc. Now, before we get to this function's name, okay, without even knowing its name, we already know all sorts of stuff about it because of properties of inverse functions. For example, we're going to call the inverse function g for the moment. We know that if you compose 2 to the x with g, you're going to get x. Okay, why is that the case? Okay, because we know that f of f inverse of x, okay, has to give you x. That's the composition property of inverse functions. Okay, so once we know who g is, we'll have a property that will work for us. Okay, we also know it works the other way. So f inverse of f of x also has to equal x. So when we find this new function g and we plug in 2 to the x, we know that we're going to get x as a result. Okay, 1, 0 has to be on the graph of this inverse function because 0, 1 is on the graph of 2 to the x. Okay, and we know that x and y coordinates flip. This new function will have domain 0 to infinity and range all real numbers. Okay, why? Because 2 to the x had domain, all real numbers, and range 0 to infinity. And we know that those two things flip when we have inverse functions. That's 0 to infinity, not inclusive. Okay, and then because 2 to the x had a horizontal asymptote of the x-axis, g, this new function, will have a vertical asymptote of the y-axis, also known as the line x equals 0. Now, we'll come back to this slide in a few minutes to fill in some more of those specific details, but we already know a lot about this new function based on what we know about inverse functions and based on this graph here. So what do we call this new function? Well, if we were trying to find the inverse function algebraically, we've been taught to take your function and write it as y equals. So in this case, y equals 2 to the x, and then we flip the variables. So now we have x equals 2 to the y, and then your goal there would be to solve for y, if you could. Now at the moment, we don't have the vocabulary to solve for y. I have no operation known to me that we've talked about so far this year that could get y out of the exponent. So you might try to translate this and say, okay, in English I would say y is the exponent of 2 that gives me x. That's how I might try to translate what I have over here when I say x equals 2 to the y. Okay, y is the exponent of 2 that gives me x. And if you try to translate into mathematics, you might say y equals exp for exponent, and maybe you put a 2 down here to stand for the base, and then you're going to put the x up here to stand for the answer. And that would be a reasonable approach to naming this new function. But what happened in 1614 is John Napier used a few Latin words and put them together and came up with this term he called a logarithm. And to shorten that, we use the word log. So instead of writing y equals exp to x, we write log for logarithm. We put the base down there, and we put the answer up here. Okay, and this is red. Log base 2 of x. And it's important that we say of, because this is not multiplication up here, as many students will try to create throughout the year to make things convenient. It's not multiplication, it's a function, and it's asking you to find an exponent. So in general, we want to say that a to the x has an inverse function, and that inverse function is called a logarithmic function called log base a of x. Okay, so all exponential functions will have this inverse function, which we call a logarithmic function. Now let's do a couple calculations to get familiar with this and not be all mystified and intimidated by this new notation, this new function. So log base 2 of 2. Okay, what does it mean? Okay, it means 2 to some exponent gives me 2. Well, that's easy because that 2 is 2 to the first, so that exponent has to be 1. Okay, so log base 2 of 2 has to equal 1. If I think about these in terms of exponents, I think I'll be okay. It's not going to be that big of a deal. What about log base 2 of 5? Let's talk about what it means. It means 2 to some power equals 5, and I don't know exactly what this number is, but here's what I do know. I know 2 to the second equals 4, and I know that 2 to the third equals 8, so this number has to be somewhere between 2 and 3. If I had to guess, it's probably closer to 2 because 5 is closer to 4 than it is to 8. So, without a calculator, I would just say, hey, log base 2 of 5 has to be less than 3 and bigger than 2. Calculator will give me a bunch of nasty digits that will give me more or less the exact answer, but for now, that's what we're going to talk about. Log base 2 of negative 1 means 2 to some power gives me negative 1. And no number that I know of will give me an answer of negative 1 as an exponent. So, turns out, log base 2 of negative 1 is undefined. What about log base 2 of 0? What does that mean? It means 2 to some power has to equal 0. Once again, that can't be done. The natural answer is to say 0, but 2 to the 0 is 1. If I think about it, I know exponential functions never equal 0, so this can't happen. So log base 2 of 0 is undefined. So I got two more real quick. Log base 2 of square root of 2 and log base 2 of 1/4. So what does this mean? This means 2 to some power has to equal the square root of 2. I don't like that, but I can rewrite the square root of 2 from chapter 1 as 2 to the 1/2. And so 1/2 is the exponent that I'm looking for. So log base 2 of the square root of 2 will equal 1/2. And over here, I don't like this one at all. But what does it mean? This means 2 to some power equals 1/4. Somehow I have to relate 1/4 back to 2. So I can say that 1/4 could be 1 over 2 squared. And that could be rewritten as 2 to the negative 2. So the number I'm looking for there is negative 2. So log base 2 of 1/4 is going to be negative 2. All right, let's go back to this page here, and let's fill in some details. We now know that the function g is called log base 2 of x, right? And so what can we fill in here that maybe we didn't know before, that maybe looks not so familiar? So this says that 2 to the g of x, so 2 to the log base 2 of x should equal x, okay? And that does not look natural. That doesn't look nice. That's not obvious. So this is one of these things I'm just going to have to accept moving forward because it's not obvious. But this means that when I have inverse functions and I compose them, I'm going to get x as an answer. The next one is a little bit more acceptable, believable. This one says that log base 2 of 2 to the x is also going to equal x. And that one's more intuitive because if I go off to the side here and ask myself 2 to what power would give me 2 to the x, the natural answer there is x. So I feel better about that one. This first one, though, I probably got to look at that a few times to feel comfortable with it. Okay, this says that g of 1 should equal 0, so log base 2 of 1 should equal 0. Do we like that? 2 to the 0 power equals 1. Yeah, I like that. That's good. All right, what about this? Log base 2 of x, okay, which is basically going to be our parent function for all logs. So all logs will have these properties, right? Has a domain of 0 to infinity, not including 0. We already saw you can't plug in 0. Can't plug in negatives, okay? And a range, all real numbers. Log base 2 of x, along with all other parent logs, has a vertical asymptote of the y-axis, or the line x equals 0, if you like. If we go back and look at this picture, we can see all those properties verified. 1, 0 is on the graph. Domain is all real numbers bigger than 0. Vertical asymptote is the y-axis. The range is all real numbers. This graph does not level off. It continues to get large, even though it doesn't look like it. And this graph increases for all numbers just like this graph does, but does not increase as fast. Okay, last thing we want to talk about here is two special logarithms that come up a lot of the times. So the first one is log base 10. This comes up a lot in science because in science you deal with big numbers that are powers of 10, and so using logarithms of those numbers comes in handy. So we call this the common log, and to abbreviate it we just write log instead of log base 10, and we just understand that when there's no argument written down below that the base is automatically going to be base 10. Okay, so there's a little equation I would write just for clarification purposes. And then the other one that comes up a lot, mainly in calculus, and since we're going to calculus, most of us, we're going to see it a lot, is log base e. Okay, let me make sure I write that as a subscript so there's no confusion here. Let's go log base e of x. Okay, this is called the natural logarithm. You could say because it comes up in nature, which might be believable or not believable to you. Okay, this is big in calculus. And remember, e is this number, my favorite number, which starts off 2.71818. Okay, and the abbreviation for natural log is going to be ln of x. Not NL, because in Latin we put things backwards, so this is Logarithmus naturale, ln of x. Just understand, don't make a big deal about it, it's log base e, and e is my favorite number, which starts off 2.718. Okay, so go back to your objectives. The existence of an inverse function to an exponential function we showed is called a logarithmic function. We talked about the properties of this function, including its graphical features. You're going to need those features to transform graphs with transformations that we've seen. And then evaluate values of the function by thinking about logarithms as inverse functions to exponentials. Think about them as exponents. And I don't think we'll be mystified or intimidated by these.